So tonight, now somebody's going to call me, I know, to make me go. Anyhow, so this is the thing where the methylation in the presence of an attractant, the MCP proteins will receive methyl groups. But the methyl groups have to come from somewhere. So the donor for the methyl group is SAM, S-adenosylmethionine. SAM is perfectly okay. So transferase is activated by the attractant. Transferase removes the methyl group from SAM and brings it over to MCP. That's what the enzyme does. It transfers. It transfers the methyl group from SAM to MCP. In the presence of a repellent, then esterase is activated, and esterase picks up the methyl group from MCP and brings it back to the SAM, brings it back where it started from. So with an attractant, you get methylation. With a repellent, you get demethylation.
Is it just CP before the methyl group is
I'm sorry?
Is it just like CP before the methyl group
CP
is
for
added?
CP.
The MCP is does it already have a methyl group before another one gets added?
Yes, I think I see where you're going. I'm going to rephrase your question, but she's asking, I think, could you have a repellent before you have an attractant? Yes, you can. There are methyl groups already there. So you could start off with a repellent, or you could start with the attractant. So you can start either way. There are methyl groups already there before you do anything. So you could have the attractant come first. You could have the repellent come first. Either way.
I understood the question as the MCP. Does the methyl refer to methyl already inside of the MCP? Or
Yes, it can be.
Okay.
Yeah, it can be. Or it might be getting some new methyls from the SAM. So either way,
Still.
yeah, there will be some already there. That's why you could do a repellent first.
But if there weren't any there, wouldn't it just be?
If there were no methyl groups there, then a repellent would be useless. A repellent wouldn't do anything. Because the function of the repellent is to demethylate. If there are no methyl groups, you can't demethylate.
But you can still methylate it.
Yeah, but but that's adding methyl groups.
Right.
You can add those all day, but you can't demethylate. Yes?
The reason why you methylate it is so that it can tumble?
No, the methylation tells the flagella which way to rotate.
Oh, okay. And then,
If you add the methyl group, that tells the flagella rotate counterclockwise.
right.
If you demethylate, if you remove the methyl, that tells the flagella rotate clockwise.
And then, so then what's, I don't understand that SAM and MCP are just different.
They're different parts of a membrane, of a protein.
Oh, okay.
Just different parts of a protein. The SAM acts as a methyl donor. Methyl groups can be taken from the SAM. Remember, S-adenosylmethionine. So it's actually an amino acid in the membrane, in the protein.
Okay, amino acid inside of the protein.
Amino acids make proteins. And they contain methyl groups. So the methyl group is literally being carried from the SAM to the MCP. Or back. With the attractant, the methyl group is coming from here to there with an attractant. With a repellent,
Did you say
it's
what the
coming
S stands
from here back to here.
Did you say what the S stands for?
So
I forgot. Yeah, he did.
is that on the flagella itself? Or-
No, it's in the cell membrane protein. It's in the membrane protein itself.
I guess what we're trying to ask is what is the bigger picture?
Well, that's what the maltose thing was. The maltose gave the bigger picture of trying to unwrap the, let's say I haven't gotten there yet for tonight. But the maltose thing is what is the bigger picture. still have to understand about the methyl groups coming and going. You have to know that. Is that part okay? The methyl groups, Jenny?
Okay, so then what about the, MCP?
What about it?
What, so then what is it?
That's a protein in the membrane.
Okay, so there's two different proteins.
No, the SAM is part of the same protein.
Oh, it's part of the same protein?
Uh-huh.
And then the MCP is.
The entire protein. But the SAM is part of that protein.
What?
Okay,
Say that part again.
okay, methionine is an amino acid.
Yes.
Amino acids make up proteins. Well, the SAM is an amino acid basically in the MCP protein. Protein, MCP is protein. It's made up of amino acids. The SAM is one of the amino acids.
The SAM is part of it.
Yeah.
So the SAM makes up the MCP.
It's part of it, part of it. It doesn't make up the whole thing. It's just one part.
That's why there's CH3 on the MCP already.
So an SAM plus a methyl group is an MCP?
No?
What else do you need to get an MCP and an SAM?
A lot
Okay,
of
here will be a
amino
protein. This will be a protein.
Okay.
So there's an amino acid, there's an amino acid, amino acid. All amino acids. That's what a protein is. Well, one of these is SAM. One of these is SAM. And so on. There's lots of amino acids. The SAMs are just one among many. Although again, it's not just methionine, we've also got the sulfur and adenine attached. But basically,
That's what the
it's
S
methionine.
stands for.
So here's the methionine, there's the methionine, probably others. Any one of those can be a methyl donor. And that will go to a different part of the MCP protein.
Either methylate or demethylated.
Well, if it's methylating, it's coming to. If it's demethylating,
Then it would be
it's going back.
going away from.
So what does the SAM become after it's lost?
Demethylated.
Demethylated.
Yeah, you just lose the methyl group. It's basically just kind of a storehouse. It receives methyls, loses methyls. Pardon me?
Ah,
So the methyl just comes and goes.
so it doesn't change the molecule?
Not really. Remember, not every protein is allosteric. The MCP is, but not the part that we're working with here. This part is not allosteric. The rest of it is. So the part that's going to change, which is coming up later, that's the part out here. The SAM does not change shape. That part of the protein does not change shape.
So then what's really a methyl group? It doesn't make a difference whether you have it or not.
Well, the methyl has to come from somewhere. We don't really care about the SAM. We care about the MCP. The methyl group is not affecting the SAM. It's a storehouse. What it's going to affect is the MCP part over here.
Does a lack of a methyl group affect the MCP?
No. No,
Why
it's
does it
only
affect-
adding or removing that affects anything. It's adding or removing from, see, let's put it this way. You know that adding the methyl groups, methylation, will cause the flagella to rotate counterclockwise. If you're not adding anything, but methyl groups are already there, nothing happens. Methyl groups already being there does nothing. It's meaningless. Only adding methyl groups or removing methyl groups, changing the number, that is what causes the effect.
So does the bacteria just swim if
That
nothing
just
is
runs
added?
along. Remember, the whole point of this is a stimulus.
Right.
But if there's no stimulus, then it just swims around.
So it's more the addition or subtraction, nothing to do with.
Changing the number, yes.
So,
Changing the
so we
number.
use maltose as an example, and then last Tuesday we said that maltose binds to the allosteric protein,
Yes, the MCP.
MCP.
But
So
the
the
allosteric
MCP, so
part.
we need the allosteric protein to have the methyl group
Correct,
in order for it to change. Okay.
Correct.
So and once it changes, it sends a signal to the bacteria basically to stop tumbling so much because it's reached its like
Because it's got an
its reward
attractant.
or
Yes,
whatever. Okay.
yes, yes.
Does the methyl group from SAM go to another specific amino acid or just somewhere else on,
Glutamyl residues, glutamic acid.
okay, on the MC? Okay.
It's very specific. Glutamic acid.
Okay.
Anything else?
Not yet.
Well, look, poop fast, I'm not worried. So, let's go ahead and continue. So again, methyl group coming from here to there, both part of the same protein, but different parts. The MCP is going to receive the methyl group, and maybe I can now say just a part of the MCP is receiving the methyl group from the SAM in the presence of an attractant with the repellent. The methyl group comes back, that's all. So it's just going here, coming back. That's the whole cycle. So with the repellent, get demethylation, esterase. So know about transferase and esterase. Transferase is what gets activated with an attractant. Esterase gets activated with the repellent. So, for the exact model, and this is where I really started losing everybody, I think. I looked at maltose. Nothing magic about maltose, it's an attractant. So all attractants do the same thing. So maltose will get through the cell wall, through a pore, formed by porins, will bind to a specific receptor molecule, which is maltose binding protein. Maltose binding protein. The maltose binding protein is allosteric. So that entire molecule is going to change shape. I was comparing that to a light switch. You know, up, down, turn the lights on, turn the lights off. So normally the binding protein is inactive. But once it changes shape, because of maltose, once it changes shape, it becomes active. And in becoming active, it can now bind to the MCP. It normally will not do that because it's inactive. But the active binding protein does bind to MCP. So the whole point of maltose, the whole point of the attractant is to activate the binding protein. And the active binding protein attaches to the MCP. And that makes the MCP change shape. MCP, at least most of it, is allosteric. Most proteins would be kind of like that, tertiary molecule. Most are like this, all bent and twisted and folded up. Most of the amino acids are inside. Once the binding protein attaches, so that's your activator molecule. Once the binding protein attaches, then the MCP changes shape, and in doing that, exposes amino acids that were buried. Because they were inside. Now they're not. And specifically, most of these are glutamic acid, or I'm perfectly okay with glutamyl residues. Either one's okay. But the point is, glutamic acid is an amino acid, part of the protein, and it is the specific receptor for the methyl groups. So with the attractant, you get methylation. The methyl groups have to bind to the MCP. But specifically, they're binding to the glutamyl residues in the MCP. So all of these here, or at least most of them, are glutamic acid. Methyl groups will come here. And then sooner or later, of course, you run out of glutamic acid. Your receptors are all filled. So then adaptation occurs. You cannot receive any more methyl groups, therefore no more reacting to the stimulus. And adaptation occurs, everything goes back to normal. Then if you add more stimulus, then it unfolds some more, the whole thing repeats, and it just keeps going until you get to the end of it. I mean, sooner or later, you've exposed all the glutamic acid, sooner or later. So once that adapts, once you've saturated all the receptors, then you're done. You can't do anything more.
You're done as in the bacteria gets to the final destination, or you're done
No,
as the
nothing
bacteria.
about destination. It stops responding to the stimulus, whatever it is.
It's uncoiled, right?
What?
It's all the way uncoiled.
Yes. Yeah, so there are no more receptors available. Remember, it's not having methyl groups present, it's having methyl groups added. Having methyl groups there literally means nothing. But you're adding methyl groups. That's what causes the response to the stimulus. Or removing methyl groups. Yes.
Do they all unwind to the same amount? Do they all have the same?
Different proteins, I mean, the same protein, same attractant, yes. But if you had different attractants, different whatever, yeah, you can have variation.
Different attractants kind of.
You bet.
different strengths?
Yes.
What does
Yes.
this have
Yeah.
to do
It's
with
not all the same. She's asking if it's always exactly the same. And I said no. It depends on the exact attractant and the exact bacteria and so on and so on. So there's always room for some variation, but the basic concept is the same for all of them. Oh, I'm sorry.
I'm trying to figure out, okay, so with the tumbling, is that separate from when it starts to go in a different direction? Is that different from when you actually have the maltose binded to the,
Well, the maltose binding to the binding protein causes the bacteria to tumble less. So it is related. So with no stimulus at all, the bacteria will tumble every couple seconds. I mean, that's just what bacteria do. With the attractant, it seems to be able to focus more somehow. So it only tumbles every like 4 seconds. So it is related.
I guess the reason I'm a little confused is because before I thought it was like this bacteria getting closer to the fire or.
Okay, now
I
you're
think it's
confusing
looking
two
for-
things.
Yeah, that's what it,
Yeah, I mean, this has nothing to do with the fire.
okay.
I'm just
So-
talking about a general stimulus, any stimulus.
So, I thought the fire was the attractants. That's what I
Oh,
thought it
yeah,
was.
but that's just one example. I'm still talking about any stimulus. That as there's stimulus, you're going to keep adding methyl groups. But sooner or later, you will run out of the
Okay.
glutamic
So is
acid.
the maltose, is that an attractant?
Yeah, bacteria like sugar too. I can tell you're still not quite clear on
Yeah,
this,
because
but I'm not sure why. What are you not clear on?
I thought the stimulus is added and then it's getting closer to that stimulus.
See, that's
Going
why
to the
you're still
direction.
getting mixed up with this campfire
Yeah.
thing. The campfire thing is just one example of a stimulus. There are many stimuli. Maltose is another one. And so let's say you're given some food. You're
Yeah.
given food, you eat it, and then you feel great for a few seconds, and then you go back to normal. So you're given some more food. So you're not going anywhere, you're just getting food. And every time you get food, like drinking coffee or something, you get an energy boost, and then you go back to normal. But sooner or later,
You'll be full.
yeah, you're full, and they can still give you sugar, it won't matter. And for the campfire, if you're trying to get close to the campfire, but the receptors are all filled, you're done responding. It doesn't matter where the campfire is. You're responding to the stimuli by adding methyl groups. And once you can no longer do that,
You're done.
you're done. You're done. And it doesn't matter the campfire, the glucose, or anything. It doesn't matter. Yeah. I'm sorry. The what? Oh, I'm sorry, glutamic acid or glutamyl residues. Yeah.
The more it's exposed, that decreases the amount
The amount of what?
of information.
Say that again. What?
Then it decreases the amount of, said,
The more that you expose the glutamyl residues, the more you're able to add methyl groups. The more you add methyl groups, the more it responds to the stimulus. The more rotation you get. So adding the methyl groups causes the rotation, or causes the counterclockwise rotation. You can only do that as long as you have glutamic acid, the glutamyl residues.
Right, so
Once you run out, then you're done.
when you run out of what?
The glutamic acid.
That's what I- Okay.